We are going to have an abbreviated acting session. Enjoy it. Hi, everybody. I'm Dean Zeller. I'm mentoring 2 students this semester. You saw Will yesterday, and Bill is Ben is a second student. And he's going to be doing a project for you on computer vision and augmented reality. We're the advanced E2 level in the computer science. Take it over, Bill.
Hello, my name is Benjamin Perkins, and my research was on applications of computer vision and augmented reality. So first of all, what is computer vision? Computer vision is an interdisciplinary field which uses programming to interpret digital content such as photos and videos. This digital content is then fed through so that you can create decisions and classify these images. As you can see on the right, this is a form of computer vision using something called detectors, or in other words, those tiny little circles right there. Those tiny little circles are measuring, looking for motion and of an object and the general shape of a human in this image. As you can imagine, this is very useful in fields such as robotics, medicine, and data analytics. Another one is augmented reality. Augmented reality is kind of a buzzword nowadays, but basically it's any technology that augments our real-world environment with digital content such as those photos and videos, but also 3D models. The important part of it is it incorporates computer vision, mainly because we need to know, in order to layer these parts onto the real world, we need to know what objects are in the real world and how we relate to these objects. This is also very important in many fields, but specifically entertainment in the form of Pokemon Go, which was a fad last year, where users could catch animated characters over the real world, as well as business, where both customers and designers can see what they are buying or designing before the actual resources are spent. Kind of a try before you buy sort of scenario. There are a lot of current implementations, but the main highlights here are medical imaging, crowd and traffic control, entertainment, robotics, autonomous vehicles, and visualization. So many times per minute, your heart beats blood throughout your body. This is shown on your face through increase in red tint or less than red tint. Using this idea, researchers at MIT were able to use computer vision to enhance those differences and then create a program that could measure your pulse by just looking at a live video. You can see right here on the top, this is the normal video, which is pretty normal, and you can see the graph associated with it is pretty normal as well. But below, after magnifying these differences, you can see how the blood in your body could be detected. And you can see a graph associated with which you can determine the pulse from. Another instance is traffic control. This is a simulation right here of an intersection where you can see the severity and quantity of accidents in this intersection. While this is only a simulation, many ideas such as this are thought to be put into implementations by companies such as Microsoft in the coming years. Again, the topic of entertainment. This can also be applied to entertainment in many ways, including Pokemon Go, which I touched on earlier, but also Snapchat. How many people in here have used Snapchat? And how many of those people have used virtual lenses or filters that you can overlay stuff in your face? It's pretty widespread. That's all computer vision and augmented reality in action. As you can see on the left here, this is one feature of the face lock, which is pretty humorous, but it can be extended to where you can see like virtual documents on your face. This is all under that field of augmented reality. Another up-and-coming field is autonomous vehicles, such as the Tesla. technologies, mainly because you needed to detect what you needed to detect the objects in the scene, to classify those objects, as well as prioritize those objects. As you can see here, it is classifying the bikes and the scenery as background and also the cars. You can also see, if you look hard enough, some modeling this right there. Kind of creepy. Next, you can also see you can see that it is categorizing as cars with little headlamps above it, and the lights are here. And lastly, it is prioritizing them based on collision possibility. You can see in the background there's a green, which indicates that that's not very possible for collisions, so it's kind of the lower priority. There's the yellow, which is kind of somewhat higher priority. And then if you look above the bikes, you see a warning sign that shows that that's the highest priority for collision, because human behavior itself is unpredictable, so you should watch out for that more specifically. There are many other implementations, but a few of these is robotics. One of these is robotics. Well, I wasn't able to find a visual of robots moving with visual on the side as well. This is an example of what a robot would see. It would be able to see, rotating around, all the different objects and classify them in the area. So you could say, hand me my hat, and you would be able to go around until you find your hat and pick it up. Now that's pretty simple, but you can see how that could be extended into many different possibilities. Another implementation that is not often thought of is teaching. On the left, you can see now in teaching, especially in scientific fields, there's some not intuitive and microscopic topics that can't really be addressed or very hands-on learning. Using augmented reality as well as computer vision, you can see in this instance there's a code which can be converted to a camera or augmented reality glasses to show that actual atom structure right above it. So the student can see the actual electrons surrounding the nucleus as well as the nucleus itself. And on the left, all the information associated with that atom. Now, these methods are now how they're implemented in the real world is very important. But the methods there, as a researcher and a programmer, the methods of which they are implemented in is most important. There are three main ways: PAR, or feature-based detection, foreground segmentation, and contour detection, which works in conjunction with that foreground segmentation. First of all is feature-based recognition. Now to recognize a face, there's a lot of different features and parts associated with it, such as your eyes, your mouth, your nose, your cheeks, your eyelids, etc. You can tell that would be pretty difficult for a computer to think of and recognize. However, using these methods, a computer makes rough generalizations of areas, so either a lot darker or a lot wider than certain areas, and generates features based on that. So lines, edges, corners, intersections, etc. And it can use that data further to detect those features in other objects. You can see an example of lines here, 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 where there's a slightly darker area, and then a slightly wider area, and then a slightly darker area. That is what the computer can interpret as a line and use that in the future. This is also the kind of classifier that you would need to input a lot of positive images or images that contain only the object you're wondering about. So in this case, a face, and a lot of negative images, so images that contain anything but the object you're looking for. In going through this, it would look for all the features in those positive images that we're looking for, and then look for what's missing in those negative images, and then it would know what to look for in general. The next one is foreground segmentation. Well, that sounds kind of advanced. It's basically just removing the background from the scene so that we know we can see what the actual object we're looking at is. There are a few steps to this, but first of all, of course, you just need to remove the background. So after removing the background in this instance where there was a tennis player on a tennis court, you can see there's a lot of interference. Now that's not very desirable because that's not the object we're looking for. So in order to get the object itself, the tennis player, you need to remove that interference. After that, now that we have just a black and white image of where the object is in the original image, we can then combine that with the original image to show only our object, our desired object. That's how foreground segmentation works in a nutshell. Next is contour. So what is a contour? A contour is a continuous line that surrounds any surface. So in this case, a hand. Combining foreground segmentation, as you can see by the white and black image on the left, contour detection algorithms are used to outline this hand. As you can see on the left, there's also some interference there, but there's no contour surrounding it because there's no continuous nature to those. So in my research, I implemented these in a few different ways. For the HAR, or feature-based recognition, I use that to detect the faces, again, because of the high multitude of possibilities to look at, such as the eyes, the mouth, etc. For foreground segmentation, I use to detect the hand, I use foreground segmentation, since rather than having to look for specific features, you only need to look for a general shape of the hand. So it's a little bit easier to visualize. And in order to keep the object itself removed from the background, or just subtract that background from it, I had to detect the user's skin tone. This was created by a custom calibrator, so I put my hand up and calibrated which skin tone I have, and then it used that to remove the rest, everything but my desired skin tone. Then drawing contours around that white and black image, you were then able to distinguish the shape of the hand and the location of the hand in the picture. This can be shown in a few steps. First of all, this is the original image. Obviously, nothing's done with it. Next, it's fed through a filter, which is making so that computers can read the hue, saturation, and brightness of a image. It looks pretty odd, but that's what it actually is. Then, using the custom calibrated skin tone, I removed everything else but that skin tone to show only the parts that are of my calibrated skin tone. In this case, my hands, but all of my face are not that different. You can then see you can then see that using that white and black image, it then draws contours around that hand so that you can, and a blue bounding box so that I can get a further estimation of the area. You can see this here as I put my hand into that, fully into that green rectangle and calibrate it. You can then see that it is detecting my hand and overlaying a firewall, which I added for a little bit of glare. You can move it around, you can resize the firewall, you can even change it between hands. But this is basically the same simple steps of all augmented reality. It's recognizing the object that we're desiring and it's overlaying a virtual image on that so that it can be used for, in this case, entertainment uses. So next, future development. In the future, I plan on implementing better algorithms so that to detect the hand itself. As you noticed at the beginning of that video, it detected my face, and obviously that's not what I was going for. In the future, I would have it so that it would look for specifically a 5-pointed object, in this case, a hand, and then also for the spaces between the fingers, which could even increase that detection more. I would also increase the skin tone calibration so that while it works pretty well right now, it can detect whatever skin tone is originally put into it. There are some backgrounds which, if they're similar enough, it will detect that and it will work as well. So improving that detection is very important. I would also enhance the user interface or how the user interacts with this program so that it's a little bit more easier for people who are not leading to use this. And lastly, I would also possibly release it as a open source entertainment package so that other developers and all the other people could read the fruits of my research and use it well for their own. Here's some of my references. And my image references. First of all, I would like to thank the Adolf Hitler's Foundation for sponsoring both my research and my attendance here at FSI. I would also like to thank Lori Ball, the Frontiers of Science Director, for allowing me to get into this camp in the first place, but also just the guidance and the help and all that she does. I would also like to thank my mentor, Dean Zeller, for giving me kind of a forward path for this research and keeping me on that path. I would also like to thank my advisor, Namita Saad, for helping me specifically with my paper and my poster and editing and formatting. And lastly, I would like to thank the FSI staff for helping me in general, just getting me here and helping me, always being helpful for every need. Now I would like to ask, are there any questions?
Yeah.
Sure.
I have a follow-up.
I actually am not. Yeah, I know. That's so that I can remove the macros successfully, so that I know specifically, like, so that I know, because obviously people have a wide variety of skin tones, and so I didn't want to just calibrate for a certain range of white skin tones. So having that calibration unit is there so that it can calibrate the user's skin tone, but also remove everything else that does not line up with that skin tone. So it's a little bit easier than looking for an object that has moved with the shape of the hand. You just have to look for something that in that general skin tone that looks kind of like a hand. Okay. So it looks like it really doesn't take that long. The majority of the first part of the video is we just like trying to fit in there and like trying not to move as much while I press the C button. It just, as soon as I press that C button, that's when it calibrates. And that's when you can see that it changes. It removes the rest of that text. Shane?
On motion analysis, we have something called perspective error. This occurs when we use a two-dimensional camera system. And with one camera, one eye. And what happens is we lose the ability to have an additional perspective and deal with that depth perspective. You feel that this should be limited at all by this theory, it's outside the idea of perspective error. And because of that, is there any way that it can improve how you're actually capturing the data and certain.
So for this specific system where I'm overlaying a fireball, it is kind of limited because at the moment I'm looking for the largest contour, so in other words, the largest object on the scene right now, which is why my hand is kind of sticking out and my face is kind of farther back in that video. But by enhancing the algorithms to detect more specifically what the hand is, I wouldn't see that being too much of a problem unless I aim for more 3D models or different sorts of assets.
So why is the green background make it easier for the program to detect the models?
So the question was, how does the green background make it so much easier for the detection? And it's mainly because green is farther away from anybody's skin tone, ideally. And so it's kind of, it should at least ease that pain of having any background experience.
Jay?
When you were talking about virtual reality and augmented, self-driving cars using it to like register cars, how do those machine vision, like how do they account for all the different colors of cars and things like that? Not gray and cars.
So there are a lot of different filters you can put on to choose one image. Like here, this right here is called an HSV filter, filter, which again is hue, saturation, and brightness. I don't know why there's a there, but there's many different ways that you can account for this. For this, the hue, saturation, and brightness was so that I could, because those are the most important parts of the skin tone. But you can also take the original image, which is a red, green, blue, or RGB value system, so that you could actually read the colors themselves. It's usually a combination of different features. So after detecting the objects, then you would use the colors and be like, you would use the original image and say, that is this color color. Theoretically, yes. For mine, I use my laptop camera, and I also have a Logitech webcam that we got from that line. So there is, you can implement this in an app setting very easily, but that was not for them.
So if you were to like have like both your hands into the brain at the same time, you're like far apart, not like under with the fireball, like stretch out the window, or would it switch to the window?
So the question was, if you had two hands on the feet with the fire, how would the firewall work with that? Mainly, because again, it's not really detecting the hands at the moment. It's mainly detecting the largest contour or continuous line. And so whichever hand is largest at the moment is where the firewall would go, because there would be no continuous line between them. But as you saw, that I kind of put my hand next to each other and pull back so that it seems as if I would transform the firewall. Yeah. So Snapchat uses a similar form, but kind of different. They use the feature-based recognition to identify the different face there, but they also use a different sort of system where there are different contact points throughout it, and they use machine learning as well as just human to see where those contact points are, and they use that to identify if a mouth is open, and that way they can also overlay some more stuff. It's more specific because it's kind of a 3D map using those contacts.